we wanted to look now at not the simple acetal, but a mixed monothiolacetal. So instead of two oxygens, an oxygen and a sulfur. And we were able to prepare this in a few steps from cyclopentanone by standard chemistry. We alkylate here, then we do a Reformatsky addition into here. We close the ring, we substitute in sulfur, and then we convert the ester into a diazoketone. And with copper catalysis in 80% yield, we get this ether-bridged 8,5 ring system with much more, that should be a much greater than 11-to-1 ratio of diastereomers at this center, where the major product is the product of retention of configuration at the sulfur substituted carbon. We don't have to have sulfur there. We can have, for example, a methoxy group, and once again, this goes in high yield, and now in this case with complete retention of configuration at the anomeric center. We can also do the one smaller ring here, and now in this case we generate the metallocarbene, and we get 3 products out in significant amounts. These two you'll recognize just differ in the configuration at the sulfur substituted carbon. So our presumption is they both come from this oxonium ylide, and then during the 1,2 shift, there's apparently more time for this biradical to randomize by bond rotation in the smaller ring than we had in the 6-membered ring. And so we see minor but significant amounts of the epimeric product, the product of inversion by the migrating center. This is the product of retention. But what about this case? Here, look at the sulfur and the bridging oxygen. They're actually switched relative to each other on these 2 cases. Now we have a sulfur next to the carbonyl, and the oxygen is at the beta carbon. So we think this actually comes from a different ylide entirely, an ylide not of oxygen, but of sulfur, where we've made this sort of medium-sized sulfonium ylide, and now 1,2 shift of the oxygen substituted carbon, effectively a ring contraction, gives us the 7,5 system with a different substitution pattern. And we're seeing that in this case because now the metallocarbene side chain and the sulfur are cis to one another on this 5-membered oxygen ring. So this can reach around and attack the sulfur in competition with the oxygen. Now, it's really good to use the mixed monothiolacetal because, first of all, that sulfur really supports the 1,2 shift. It seems to be a very good stabilizing group for whatever mechanism you believe that 1,2 shift happens by, but it serves another purpose after the 1,2 shift to allow us to open up this bridging ether with complete regio control. So if we remove this carbonyl from the picture by ketalization, we can break open this bridging ether either by a direct reductive elimination using lithium diterbutyl biphenylide as a single electron reductant to generate the organolithium here and then pop open the ether to give us the alkene. Or if we want a little more functionality, we can oxidize the sulfur up to the sulfone and then just using base eliminate this open to give us the vinyl sulfone. So for dactylol, very, very similar situation, except we need a methyl group on the 5-membered ring with control of absolute configuration. And also we need this geminal dimethyl group. So incorporation of the methyl is easy. We start out with puragone, and this is known chemistry. We can convert this into this ketoester using a Favorsky rearrangement. And then in 2 steps, introduce this 3-carbon side chain. Reformatsky addition goes with very high facial selectivity. Ring closure with BF3, sulfur exchange gives us this, and then conversion of the ester to the diazoketone using the standard 2 steps gives us this substrate. And this is the work of Graham Murphy, who was my first University of Alberta PhD student. He's now a postdoc at University of Colorado with John Wood. And Graham took this compound and subjected it to our standard conditions, and in excellent yield and complete diastereoselectivity, we got this product. And furthermore, he found he could do a methyl addition into this ketone, and then the LDBB reduction to give us this diol. And with PCC, of course, two tertiary alcohols, neither one will oxidize, but this tertiary alcohol is allylic, so we can do the allylic rearrangement of the chromate ester and end up with the allylically transposed enone here. This goes in reasonable yield. Our thought was, with this ketone installed, first of all, we put the double bond in, the tri-substituted double bond, right where we need it. We have our angular hydroxyl. We have our correct array of stereocenters here. We just need to put in the gem dimethyl group. We were going to use this ketone as the means to put in the methyls. Unfortunately, as soon as we did this PCC rearrangement, this angular hydroxyl did a transannular closure to give the hemi-ketal, and this is a dead end. This compound has no enolate reactivity at this center. So under no circumstances were we able to methylate. And that caused us to revise our thinking about how we were going to introduce this geminal dimethyl. So we went back to this series, now with a T-butyl ester instead of a methyl ester, and that allowed us to take off the T-butyl and make the carboxylic acid. This is the work of Jeff Johnston, one of my current students, and Jeff can then esterify this with this allylic alcohol, which sets us up for a decarboxylative allylation using palladium catalysis in order to give us this key intermediate. And now this intermediate can be subjected to a rhodium-catalyzed Reformatsky addition, and then we deprotect the silyl ether and convert it into an allylic bromide to prepare for ring closure now to give us this pyran ring. So notice we've got nothing up here on this carbon, but we still expect this to rearrange because this is an allylic ether. And so this is set up to do a 2-3 shift. So we can convert the ester to the carboxylic acid as before, and this goes quantitatively to the 8,5 system, where now we have an exocyclic methylene group where we eventually want the gem dimethyl. We can add methyl grignard into this ketone and then do a modified Simmons-Smith cyclopropanation to put in the extra carbon that we need, and then hydrogenalyze open the cyclopropane to give the gem dimethyl. So you can see we're now very close, but unfortunately, lacking any sort of sulfur atom here, we don't have a good means to open up this bridging ether. We can't use this tertiary alcohol, and we went back to this stage and found that we also couldn't use the ketone to selectively break this carbon-oxygen bond. So now Jeff has gone back to here, and he's putting the sulfur in to ask the question, will that do a 2-3 shift or a 1-2 shift? If it does a 1-2 shift, then we should be able to finish dactylol very, very quickly. Next, I want to take you back to this slide. Remember, we talked about this before. We got 3 products with this substrate. And this product here, I said, came not from the oxonium, but from the sulfonium ylide. And I want to highlight the fact that forming the sulfonium ylide should be geometrically quite a bit more difficult. It's a 7-membered bridge system as compared with just simple closure onto the oxygen, much closer and probably less ring strain. So it still formed significant amounts of the sulfonium ylide, presumably because the sulfur electrons are just so much more available as a large polarizable heteroatom. So forming the sulfonium ylide should actually be quite facile if we change the substitution so that it's closer. And in